Today. I want to emphasize every year I teach this course I deviate more and more from the book, in the sense of not bothering to cover some things that are in the book. I encourage you all to read the chapter and incorporate it as part of the material for the course. It's very well written, it's very self-explanatory, and ideally you should read it before we discuss it in class. Then we're ready to have the best discussions. Okay, so we're talking about decision trees, and we said that they are a formalism or a representation for functions. If at the leaves you have the output yes or no, then these functions are specifically concepts, namely functions into a space of two possible outputs. And as a formalism for expressing functions, the first question you should ask yourself is, what is the expressive power of this formalism? Which is the same thing as the representation bias. So any formalism I give you, your first question should be, okay, what can I express in it? Can I express anything, any possible function, or only some of them? And if only some of them, is it the majority or a minority part of all the functions, and how can I characterize which I can express and which I cannot? So we started doing it last time. We realized that expressing conjunctions and disjunctions was easy, and conjunctions and disjunctions of n variables can be expressed with a tree of about n nodes. Unbalanced tree, yes, but n nodes only. Then we looked at expressing XOR, also known as the parity function. And somebody made the case that it looks like we will need an exponential number of nodes to express that. What about other functions? For example, suppose you have 50 binary inputs and you want to know whether at least 20 of them are turned on. So we'll call that problem at least k out of n. You have n inputs, n binary inputs, and the answer is yes if and only if at least k out of these n are on. Is this difficult for decision tree to do? So what do I mean by difficult? Can you do it with a linear number of nodes, linear in n? If not, can you do it in a quadratic number of nodes in n?
No, we cannot do it. We can do it only in exponential number of nodes.
Exponential number of nodes in n?
Yeah.
Okay, so you suggest that the problem is O of 2 to the n. Any other suggestions? Please. K times n? Any other suggestions? So how would you do it in Kn?
So if the tree starts at the top, you have to populate the entire, the whole node branch and 20 layers of yeses along the side. There'd be a row of yeses there and then nodes across the bottom.
So let's start doing it for n equal 10, just to get an idea. So you start with x1, and then presumably you ask about x2 here, and then?
And you'd have to branch every node down. Yeah, you go.
What about here?
You'd have to check x2. And so on. I mean, if it's going to be 10.
How far down?
10 deep to the right. And
Okay, so if it's 10 deep here, right, you go up to x10.
And then there'd be a yes node there. And so if you went right 10 times and then right 9 times, left 1 time, right another time, there'd be another node there. And it'd sort of be a 10 wide swath of nodes going down that way.
Okay.
Oh, well, I was going to say it doesn't need to be 10 long on the rightmost side, or 10 long on the leftmost side. On the rightmost side, it only needs to be k long, and on the leftmost side, it only needs to be n minus k long.
Yeah, n long means you inspect all the questions, right?
Yeah.
Yeah, I guess it would be n minus k.
So if you take the entire tree, which is 2 to the n, and very broadly you say that the more to the left you are, the more no answers you got, right? And the more to the right you are, the more yes answers you got. So right here, all 10 of them are on, and right here, all 10 of them are off.
Sorry, I thought you meant k was 10.
I'm sorry?
I thought you meant k was 10, not n. Anyway.
Ah, okay. So first imagine spreading the entire tree. So you have 2 to the n nodes, irrespective of k. And then let's draw the boundary of what part of it would be yes, what part of it would be no, and then see if we can chop off the tree and make it smaller. Okay? So if you need at least k, you don't lose hope until you got n minus k, or let's start on the other side. You're happy as soon as you saw k, so you're happy about, let's say k is around half. You're happy around here. If you're at the extreme side, you got k positive answers here, you're happy, you don't need to spread, you don't need to develop all of this. But if you didn't get fully k positive answers, if some of them were negative, you were here, then you need to go a little bit further. You need to make k steps in the right direction in order to be happy and not have to ask any questions anymore. Right? So this would argue for you can make as many steps in this direction as long as you can still make k steps in this direction. So you'd have something like space like this. I'm not sure exactly what the shape would be. Maybe like this. Coming from this side, as soon as you see n minus k negative answers, you also don't need to ask anymore. So that would depend on whether k is really close to half or not. The most difficult case typically would be with k is very close to half, is half. When k is close to 1 or close to n, your tree becomes smaller. So my intuition, and I didn't check it, is that the answer is in the order of n to the k. I could be wrong.
Well, for k equals 3, that's larger than the whole tree. I mean, the whole tree is n squared.
No, the whole tree is 2 to the n.
Oh, to the n, right, sorry.
Okay. So if you look at the case, if you want to convince yourself, if you look at the case of k equals 3, and just try to answer that question, there would be already a big difference. As n becomes very large, let's say n is 1,000, and k is 3, it should be very easy for you to figure out for yourself whether you need a tree that's simply 1,000 to the power of 3, or whether you can make do with something much smaller, which is 3 times 1,000. Make k equal 2. I think that will give you the answer as well. Do you need 1,000 squared, or can you make do with 2,000? Think about it. Some related questions are: exactly k out of n. Which one is harder? At least for this formalism. I'm sorry? Exactly k is harder? Why?
You always have to look at every single instance.
Not always. If you went beyond k, you don't. But once you saw k on, you have to keep asking, and you keep going to the end or until you see another one, just k plus 1. But you can also think of getting the answer to one of them out of the other. I mean, you can get the answer to this one by combining 2 trees of this type, one for k and one for k plus 1, and insisting that the one for k gives you the answer yes, and the one for k plus 1 gives you the answer no. And that's effectively the same as answering this. Okay? And then you have an even number out of n, which is the parity, or XOR. So this is a special case when you take a particular subset. You could take another subset. You could say, I want the answer to be yes if the number of inputs that are on is 1, 7, 17, or 35. Okay? You could see why that might be a little easier than even or odd, because even or odd are uniformly distributed throughout the space. So as was pointed out yesterday or last time, under every condition, every bit counts. This is an interesting point. When are arguments informative? Some arguments are never informative. Most likely, arguments, namely the inputs, most likely some inputs under some conditions are informative, namely their value makes a difference to the outcome. And under other conditions, the value does not make a difference to the outcome. So if you go back to the case of at least k out of n, and you've already observed k arguments with k inputs that are on, the rest of the arguments, you could argue, are not informative anymore. So some arguments, some inputs, under some conditions make a difference, and under other conditions, namely conditions of the other inputs, don't make a difference. XOR is unique in that every input makes a difference under every condition. No matter what the values of the other arguments are, any one argument, flipping it, changes the answer. This is an extreme case. In fact, it's the only function up to inversion instead of XOR. It's not XOR. It's the only function that has that property. So in that regard, it's kind of the hardest function. Luckily for us, the real world rarely operates like an XOR. We love to use XOR as an example to test these formalisms, and we point, we'll do the same thing with neural networks, and we'll see that XORs are really hard for neural networks, and they're really hard for decision trees. Is that a bad thing? I don't think so. I think it just agrees with our intuition that our formalisms should match our expectation of what kind of functions would be out there, and XOR is a function you find in computer science classes, not in the world. Yes, you do find it in the world in some places, but usually in engineering problems, not in natural problems. Okay, I asked you a question at the end of last class. What functions can you not express in a decision tree? Just like we had this other formalism before with the angled brackets, and you guys came up with examples of disjunctions that could not be expressed. What function can you not express with this decision tree? You can restrict yourself to binary inputs, or if you want, they could be non-binary, or whatever you want. Let's start with binary. You have n binary inputs, and you have a binary output, the concept. What kind of functions cannot be expressed by decision trees? I'm sorry? Analog. Okay, so you may be right, but let's restrict ourselves to binary inputs and binary output. Okay, so you have n binary inputs and one binary output. What can you not express with decision trees? I'd like you to form your own opinion before we discuss it, even if you don't volunteer it. Please.
Well, anything that's somewhat random, or like if you have random training data, it's very difficult to classify that according to a decision tree.
So a randomly generated function,
right.
A function that has sort of randomly chosen values for each input, will be hard Do you mean it'll be impossible, or that there might be?
It's not impossible, but it just creates a very big decision tree it doesn't classify well the data, I guess.
You're moving a little bit ahead of where I want to be. You're talking about classifying data. I'm only talking about representational power. You're saying that if you choose a randomly generated values for the function, so it's still a function. It's a deterministic function, but the way you chose it was randomly from all the functions. Chances are it'll be hard to find a decision tree that agrees, that implements it, but not impossible.
Right.
Okay. So let me go back to the impossible question.
I think you can represent every function.
Thank you. I think you all suspected it, no? Okay, so don't be shy. So, two caveats. One, when I ask you a question, I will try not to give you hints as to whether it's easy or hard. Okay? So don't judge by the way I phrase the question whether it's easy or hard question. It could be very easy or it could be an NP complete question. Second, if I ask you a question is, what functions can you not represent? It is a perfectly valid answer, none. Okay, so the way I phrase the question also will sometimes try to mislead you. The reason I do it is not to be nasty, is because when you deal with research, you don't know the answer. And you very often deal with the question of, can you find an example? Is there an example of X? And sometimes the answer is no, there isn't. Sometimes there's no solution to the problem. So I'm trying to make your life hard, but for a good cause. So yeah, I'm asking you, what functions can you not represent with decision tree? And the answer is none. You can represent any binary function with decision tree. Does somebody have a quick proof of that? Tom? Yeah, so you can go back to our fully developed tree that has 2 to the n minus 1 nodes. Okay, it's very easy to describe this tree. You have x1 here, you have x2 here, you have x3 here, and x4 in the next row, and every row has one of the x's all the way across. And at the bottom you have 2 to the n leaves. And now you fill out the correct value for each one of the 2 to the n. Right? A function is fully specified by specifying its value on each one of the 2 to the n possible inputs. And that's exactly what you will be doing here. Just spell it out here. So it's even the same tree, a universal tree that can implement all functions. The only difference is you change the labels at the bottom. As we pointed out last time, decision tree representation is redundant. That means the same function can be represented by many trees. So one representation is a full tree. But for many functions there would be smaller trees that would represent the same thing. I think you're correct that for a random function there may not be much smaller trees to represent it. Okay, how many functions are there of n binary inputs into one binary output? How many different functions? Can somebody say it really loud? Did I hear 2 to the n? Was that the full answer? How many different functions of and 2 to the 2 to the n, doubly exponential. N binary inputs means that the input space X is of size 2 to the n. Why did I write 2 and say n? I don't know. Better. And with the input space is 2 to the n, the concept space is always 2 to the x, which is 2 to the 2 to the n. How many decision trees are there with n inputs? How many different decision trees are there? A decision tree is different if two decision trees are different if they differ in any detail. Like what nodes are there, what's in each node or what's in the label. If there's even one difference, it's not the same tree. How many different decision trees are there with n binary inputs? More than 2 to the 2 to the n. I just showed you one family of trees, this full tree. Fix it with x1, x2, x3 all the way to xn, and then vary only the leaves, the values of the labels, right? Yes and no. There are 2 to the n labels. Any permutation of those is 2 to the 2 to the n. 2 to the 2 to the n ways of filling the leaves. So only this tree family is already 2 to the n. Now consider permuting which variables you ask about in each row. That's already a factorial permutation, right? And that only considers trees that are homogeneous in the way that in every row you ask only about the same input. What about you move this x3 to here and bring up x4 from there? So the space of all possible trees is huge. It's even larger than doubly exponential. And that's before we start looking at trees that are not fully branched out. So the representation power is very, very large and redundant. Is that a good thing? One at a time. Is it a good thing that it's large, that it's very powerful, that can represent every function? Yes. Why?
Because you're not leaving out any constants.
You're not leaving out anything, so your hard bias or your language bias or representation bias is not making any mistakes. It's not throwing out anything that might be needed. You're guaranteed not to make the mistake of concentrating on a part of the concept space that does not contain your answer. Okay? Tom?
If we consider all decision trees as being equally good,
Mm-hmm.
then we have no basis for generalization.
So if we don't introduce bias, we don't have a basis for generalization.
Yeah, so this makes it true that the exact range of
Okay. Do you agree? Want to add any comments? So this does bring up an important question: is why have a bias in the first place? We had a bias with the angled brackets. We don't have a bias with or hard bias with decision trees. It seems safer, as you pointed out, safer to not have a bias. Why not define our hypothesis space to be the entire concept space? Remember the version space idea? When you start with a hypothesis space and you shrink it down as you see examples. If you start with a very, very large hypothesis space, let's say the concept space, and you shrink it down, you still are left with a very, very large version space, even after seeing a lot of examples. And that, you could argue, is not so good, because you end up with less conclusive conclusions or less clear understanding of what the remaining options are. On the other hand, if you start out with a small hypothesis space, you're making an assumption. If the assumption is true, namely the target concept is in the space, the assumption is true, you're in good shape. You can move faster. It's like searching for a coin. You have a huge area outside your house where you lost a coin. You're searching for it. Well, if you make the decision that the coin must have fallen somewhere near where you parked your car, that's a bias. You stick yourself to searching in that area. If you are right, you have a much better chance of finding it because you're looking in a smaller area. If you're wrong, you won't. So choosing a bias randomly is not a good idea. It's just saying, okay, I'll just choose one segment of 10 yards in front of my house and search there. That's a bias. But if you choose it randomly, that's not a good idea. If you choose it judiciously, if you ask yourself, given everything I know about the situation, where is it most likely to be, then maybe it is a good idea. So I want to show you what happens when you have absolutely no bias. Okay? It's very striking that you have no ability to generalize. What will turn out happening, at least in the case of binary inputs, it's very clear to see that finding the correct answer for one input tells you absolutely nothing about what the correct answer might be for another input. And this is what generalization is all about. So to do that, let's see. Let me take this case of n binary inputs. x1, x2, x3 through xn. And I'm going to list out, in principle, all possible combinations of values of these n binary variables. And I'm going to list them out the way computer scientists do, starting with 0, 0, 0, 0, 0, 0, 1. Let's have xn minus 1 here. So this is 0, 0, 0, 1, 1, 0, 1, 1. And this is going to go on for a long time until I get to 1, 1, 1. 1, 1. Okay? This is input number 1, and this is input number 2 to the n. Oops, sorry. 2 to the n rows. Each input is represented by a bit vector of n bits. Okay? You're familiar with that. And now I'm going to put here all possible functions. And the way I'll do that, first of all, the line would have to be very, very long. Have to go all the way to Tanzania and back. This is going to be the first function, f1. It's going to be f2, and so forth. And I'm going to introduce a new representation for functions, which is a very simple and complete representation. The function is going to be represented by a bit vector of 2 to the n bits. That basically specifies the value of that function for each input. It's an explicit representation. Most representations of functions are implicit. They give you a formula for calculating the value of the function. Instead of giving you a formula, I'll just list all the values. You'll agree with me that this fully specifies the function. So I could, instead of using 0 and 1, I can use yes and no here to help you make a distinction between the input and the output. But between you and me, it doesn't matter. 0, 1, yes, no. So I'll start with no, no, no. Everything is a no. And here will be no, no, no. And the last row would be yes. And then F3 would be no, no, no. Again, it's a binary numbering, and there would be a yes, no here. And here there would be a yes, yes. So I'm enumerating all possible functions. How many functions do I have? 2 to the 2 to the n. Okay, so maybe I should go all the way to the end of the board to impress you with how fast 2 to the 2 to the n grows. Just think about how much 2 to the 2 to the n is when n is 10. 2 to the 10 is about 1,000. 2 to the 1,000 is... Did we talk about the number of elementary particles in the universe? We did. Okay, it's more than the number of elementary particles in the universe. So it's very, very far out. But for simplicity, we'll put it here. This is f2 to the 2 to the n. And this one says yes to everything. So I'm now going to show you explicitly what happens with the version space if you have no bias. If you have no bias, that means that you start with the version space being the entire set of all possible functions, all 2 to the 2 to the n of them. That's your version space, that's your hypothesis space. So, version space, first of all, H is equal C, and the version space of H and null, no data, would be just H, where we started. And now, you start going through your training examples. And your first training example is one of these x's. Let's say something here, xj, one particular input. And you're told that this is a positive training example. So you're told that the function must say yes on it. Well, consider all the functions in your space. Some of them say yes, some of them say no. How many say yes, how many say no? Half, exactly half. Being computer scientists, I'm sure you realize that what you have here is a sequence of no's up to the middle, and then a sequence of yes. and in the second row you'll have no up to a quarter, then it switches to yes, then it switches to no, then it switches to yes, and then the third one would switch every eighth, and the next one would switch every 16th, and all the way at the bottom you will switch like crazy, no yes, no yes, no yes, right? We all know this kind of binary counting. But one of the properties of this is that you have exact mirror image. You have exactly as many no's as there are yeses. So if we looked at position J, at row J, you will have blocks of, I guess you'll have 2 to the J blocks, alternating yes, no, yes, no. And since we're told that the correct answer is yes, we will rule out all the blocks that say no. This block says no here, we will rule it out. And here is another block that says no. Says no in this column, we will rule that out too. And there are going to be 2 to the J such blocks. We're going to rule them out. How much of the version space did we eliminate? Half, exactly half. Okay? But look how independent the different variables are in this version space. We eliminated half, but we didn't change the property of the table that the yes and no's alternate in blocks. And they're always balanced. Because the half of the table that we eliminated was exactly balanced with regard to all the other variables. Oh, I'm sorry, all the other inputs, the 2 to the n possible inputs. Now we're given another training example. This time let's say it's negative. It'll be x, if this is xj1, it'll be xj2. And since it's negative, we have to eliminate everything that says yes. So of the remaining table, we will eliminate all the blocks that in this row said yes. How much of the version space will we be cutting out? Exactly half. If you're not sure, go back and look at it on your own and convince yourself. No matter which input we get, no matter whether the correct classification is yes or no, we will always be shrinking the version space by half. Now that's not a bad pace. Remember we talked about 20 questions? Cutting things by half is pretty much the best you can do. If you think from information theory point of view, every time you're given an input, you're told if it's positive or negative, you were given one bit of information. And by cutting the version space in half, you're using that bit fully. So what's wrong with that? Right, the size of the hypothesis space is so big, it's 2 to the 2 to the n, that if you cut it in half every time, how many such steps do you need to shrink it down to 1? Log of the size of the space. And if the space is 2 to the 2 to the n, log of that is 2 to the n. So you will need 2 to the n examples to shrink it down to 1. And 2 to the n is exactly how many possible inputs you have. So you need to know all the inputs to bring it down to 1. In other words, you couldn't learn from one input about another input. You needed to see all of them. Furthermore, if you didn't see all of them, if you just saw some of them, and stopped and looked at your version space, and now you try to classify new instances by a vote in your hypothesis space, you will discover that the votes are always tied. For any input, the vote will always be tied smack in the middle. Half saying yes, half of the version space saying yes, half of the version space saying no. This is the property of these alternating blocks. So this is a demonstration that when you don't have any bias, you cannot have any learning. That knowing the value, the output of one input tells you nothing about the output of another. It's not just that you cannot reduce uncertainty to 0. You cannot reduce uncertainty at all. Looked at it from an information theory point of view, to fully specify a function over n binary inputs, you need how many bits? How many bits of information? Sorry? Log n? You think of log h maybe? Please? Say it again? 2 to the n bits. You basically need 1 bit for every possible input. To To fully specify the function, you need to basically specify what the output of the function is on each one of the possible inputs, and there are 2 to the n of them. If you're given no other information, such as a tendency towards saying yes or towards saying no. If, for example, you were told that this function likes to say yes, that, from information theory point of view, gives you some information. Right? You can talk about the reduction in your uncertainty. If you think about trying to predict that function fully, and you have a certain uncertainty, if you're told that the function tends to say yes more than no, that means that there are more yeses than nos in the answer. That reduces your uncertainty somewhat. You can look at the entropy of predicting that function, and it is less than 2 to the n bits. But if you're not told anything, the entropy or the uncertainty in predicting that function is exactly 2 to the n bits. And every example that you're given of a binary output gives you 1 bit. So you have to have a bias. This is true not just for the case of binary inputs, of course. It's just easy for us to enumerate it in binary inputs. It's true for continuous variables. It's true for just about anything. If you don't introduce any bias, if you don't predetermine something or pre-assume something, you cannot learn. You cannot generalize. You cannot crosstalk between examples. One of the things we'll be doing here is sometimes make explicit bias assumptions, and other times look at existing models or mechanisms and ask ourselves what bias are they implicitly assuming. Sometimes the assumptions are very implicit. Since we all have learning machines in our heads, we should ask ourselves also what bias do we have in our heads. When we draw conclusions, when we jump to conclusions, when we make generalizations, what underlying assumptions are we making? Question? Comment, question?
Perhaps looking for functions that can be expressed in less space compressible ones, where there's some pattern or something.
Okay, that's a good one. I mean, that ties. Let's start with a historical perspective. You're all familiar with Occam's razor, right? Or Occam's rule. So Occam was a philosopher from a long time ago. I don't know which century. I think it was the Middle Ages. And his principle in explaining phenomena by science is to try to find the simplest explanation that explains the data. Okay? And we use that very broadly in science today to say, if you have 2 theories that both explain the exact same data, one of them is simpler than the other, you should prefer that. Why? Not an easy question. Why? You can actually argue that for a long time. And maybe we will. But the suggestion that was made here is to maybe bias ourselves towards functions that can be expressed more succinctly. So, as n grows, 2 to the n is a fairly large number. And you can think of schemes for representing a bit vector of 2 to the n succinctly, maybe compress it. Maybe give it to the Unix compress function. That would be a reasonable thing to do. So functions that are, let's say, all 1 would be compressed tremendously. And those that have only a few zeros or a few nos would also be compressed well. Comments? See anything good about this or bad? Or what if you have 2 compressed functions? One by Unix and one by, I don't know, Windows. Which one should you use? Can you find a compression algorithm that will compress all of the 2 to the n possible bit vectors? Sorry? No, why not?
Because by like you can't have like a perfectly generalized compression algorithm.
Why not?
It would tend to assume something about the input stream, or otherwise, like if I just give you some arbitrary n bit vector and say compress this, then for all you know it's arbitrary. There is no inherent pattern. You have to look for a pattern in order to be able to try and compress it. You have to assume that there's some kind of redundancy that you can find. And you only have like a finite list of the types of redundancy you could possibly look for.
Okay, so there was a Russian mathematician called Kolmogorov. That dealt with this question. I hope I'm spelling it right. There's at least one F there. Somebody Russian here? Who knows? I'm sorry?
Another B.
Another B? V. Here? Kolmogorov. Thank you. Who deals with this issue of compressing bit strings. And there's a very simple counting argument that says that you cannot compress all possible bit strings, because if you did, since there are 2 to the n of them, well, let's take a bit string of length k. K is 2 to the n. Bit string of length k, there are 2 to the k possible bit strings. If you had an algorithm and compressed them all to a smaller bit vector each, if they're smaller than k, then you would, if they're smaller than k, let's say they're m, which is smaller than k, there are only 2 to the m possible compressed representations. And you cannot fit 2 to the k possible bit vectors into 2 to the m compressed representations in a way that you can restore the original. Now, it doesn't mean there's no point in compressing. There is a point in compressing if you suspect that some bit vectors are more likely than others. And then the average compression length would be less than k. But if they're all uniformly distributed or equally likely, you cannot compress them. And in fact, introduced a measure called Kolmogorov complexity, which measures in some sense the intrinsic randomness of the bit string. But I'm saying in some sense because there is an arbitrariness to it. It depends on who's doing the compression and what they're assuming. So compression is always relative to your expectation, which brings back the question of bias. If you have reason to suspect that some things are more likely than others, then compression can use that and can bring this to the foreground. But if you don't, you can't compress. So if you have a source of input that has entropy of k bits, you cannot compress it to have less than entropy of k bits. I think we discussed that when we talked about information theory and Shannon's theorem, that if the true entropy of the source is k bits, then there is no coding scheme that would use fewer than k bits on average. Right? We said that the entropy is a lower bound on the average length of average efficiency of transmitting the information. So compression, bias, prior expectation, prior distribution, complexity, they're all tied. They're almost the same thing, just viewed from different angles. And I should add generalization and learning. They're all really the same concept. Okay, we'll go back to decision trees. So, we dealt with the representation power of decision trees. We concluded that they have no hard bias, they can represent anything, but sometimes it seems that they might require an exponentially large tree. In fact, you can probably prove that sometimes they'll require an exponentially large tree by counting argument. How many different functions there are, how many nodes are in the decision tree. The decision tree of k nodes can only represent up to so many different functions, and therefore if you can see the direction of this proof. Very often you can prove these things with counting. Just saying there are only so many decision trees, there's so many functions, therefore I won't be able to represent them all, I will need the larger decision tree. The second question you have to ask yourself after asking about representation power or bias is, how do I learn a tree? Let's suppose I do make some decisions about which trees I prefer. Let's say I prefer smaller trees. How do I go about taking my training data and finding a tree that agrees with the training data and is as small as possible? So I introduced a preference for small trees, which you guys mentioned before. Preference for a small tree is another kind of bias. It's what we call a preference bias, or a soft bias. So we had hard bias, which we also call language bias or representation bias or restriction bias, and that's basically the choice of H. And then a soft bias, also called preference bias, which is something that you expressed today, saying, well, let's go for small trees. Is it the only kind of bias you can introduce? No. You can have a bias for balanced trees. You can have a bias for trees that only ask about a small number of inputs, of input variables, which is not the same as a small tree, right? And you can think of others. I can't tell you which one is better. You need to look at the specific instance and ask yourself what do you think is the correct answer, which sort of characteristics does it have, and work from that to what bias to introduce. But one reasonable bias is a small tree as measured by number of nodes. It's reasonable because it's a compact representation of a rule, of the function, and also because it will make your life easier later when you implement it. So computationally, it's a pragmatic choice to make. Let's say we made that choice. We chose a soft bias of a small number of nodes. Now we have a computational problem. We have training data, and we're looking for a decision tree that agrees with the training data and that has as few nodes as possible. Now it's a very well-defined mathematical or computational problem. In fact, it becomes a search problem, because you have the space of all possible decision trees, which is an exponentially, in fact doubly exponentially, in fact super doubly exponentially large space, and you're supposed to search this space with finite computational resources to optimize some function, and the function is the number of nodes in a decision tree that agrees with your training data. Very difficult computational problem, but we can attempt it. What do you do when you need to search an exponential space? I'm asking the computer scientists in the crowd. Split it in half. That would be very good if you could. I don't know how you could do it here, but okay. You need to use heuristics. Search heuristics. So one heuristic would be to build a tree a little bit at a time. Start by deciding what to put in the root, and based on that, look at the rest of your data and decide what to put in the right child of the root and the left child of the root. Let's try to do that. Instead of trying to globally find an optimal tree, I will concentrate on the question of what to put in the root of the tree. So I'm going to show you typical training examples, typical set of training examples, and ask you which attribute would you put in the root. So this is a problem called play tennis, which is very similar to the enjoy sport. It's a binary output. The inputs are either binary or trinary. So the classic examples we've dealt with until now. So outlook could be sunny, overcast, or rain. Temperature could be hot, mild, or cool. Humidity could be high or normal. And wind could be weak or strong. And we have 14 trading examples. And our decision boils down to choosing for the root one of these 4 attributes. Which one would you choose? More importantly, I don't care so much about which specific one you would choose, and what I care about is what argument would you use? What criterion would you use to decide which one to use? Your goal, to remind you, is to produce a decision tree that agrees with all these examples and that has as few nodes as possible.
How about whichever one's going to give us the most information on average?
Wonderful. I was hoping to get to that after 20 minutes of discussion, but you short-circuited me, that's fine. That's what I want to hear from you after hearing the discussion of lectures on information theory. The one that gives you the most information. Most information about what? So what are the random variables here that tell you one thing, tell you information about the other? Think in terms of information theory. What is the uncertainty that we're trying to reduce, and what are we going to be using to reduce it? Please?
Information about whether or not you're going to play tennis.
Okay, information about whether or not you're going to play tennis. So what is the random variable whose entropy you're trying to reduce? You're there. Play tennis. Think of play tennis as a random variable that has 2 values, yes or no. Before you know anything about the temperature, about the climate of the day, the weather, it has some uncertainty in it. How much? Sorry? How much uncertainty is in the random variable play tennis before you know anything about the day? Can't hear it.
Is it half yes, half no?
Half yes, half no? Not necessarily, but how many bits of uncertainty? Exactly 1? No more than 1. Up to 1. It's a binary variable, yes or no? You're right, if it's half-half it would be 1, but we don't know that it's half-half. In fact, if you treat this as the problem, forget about generalization. This is a definition of the function. Okay? The function exists only on these 14 examples. Then you can count no, 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 no. 5 no's, 9 yeses. The entropy is less than 1 bit. It's a 9-to-5 ratio. So the random variable whose uncertainty you're trying to reduce is the outcome, the output of the function. What are the random variables that could reduce that uncertainty? All these 4 attributes. What is our goal? Our goal is to build a tree that uses some of these 4 attributes in some combination. Maybe some of them will show up in one branch, some in the other, some will not show up at all. At the end, we will have a tree that classifies all these 14 examples correctly. That means if you take each one of the 14 and you trace it down the tree until you get to a leaf, it will give you the right answer, yes or no. A property of such a tree is that the answer here, if you propagate all 14 examples down, you will find that all the examples that end up in the same leaf agree with each other. They're either all yes or all no. Another way of saying that is that their entropy, the entropy of the outcome, is 0, conditioned on knowing that you're in this leaf. So the entropy of the output, which we'll call y, given which leaf you're in, is 0 once the tree has done what you wanted it to do. It's 0 here, it's 0 here, it's 0 in all of these. So our goal is to get to an average or cumulative conditional entropy of 0. When we start with entropy of the answer unconditional, and it's 9/14 log of 9/14 minus 5/14 log of 5/14. It's some number less than 1. That's the unconditional entropy of the outcome. And now we ask ourselves, what question should we ask here such that the average entropy here in the next generation would be the lowest? So we're trying to reduce the uncertainty of the outcome as much as we can. So if we say that the attribute we're going to use is one of these 4 attributes, call it A1. Let's say A1 is put here, and these are the 3 possible output. We consider A1, we take the 14 examples and split them on A1. We discover, say, that the middle one is what I call a pure node. It's a node where all the instances that go in here agree. If they all agree, we don't need to develop this any further. We can just give it the value, let's say yes or whatever it is, and note that the entropy under this condition, entropy of the output under this condition is 0. But the entropy here is not 0, because the node is still not pure. How are we going to calculate the overall reduction in entropy as a result of asking question A1? Entropy of the answer given A1 is sum over all possible values of A1. Okay, let's just say I belong to A1. So A1 typically in our case has 2 or 3 values. The amount of entropy that remains in Y, if you know that A1 is I, weighted by how likely AI is to be, A1A is to be I. This would be the probability of A1 equals I. This is the average conditional entropy, if you remember it from the lecture on information theory. In our particular example, I takes on 3 values. For the middle value, this part is 0. Now this part is important because it may turn out that an unbalanced number of examples go into here and go into there. We're interested in average entropy or average uncertainty. Now we can calculate this for any fixed attribute. We can calculate this value and compare it to the same thing for a different attribute, A2 or A3 or A4, and choose the attribute that gives you the smallest numerical value, right? The lowest remaining entropy. Alternatively, we can say, so let me use exactly the same notation I used last time. The winning attribute, A star, is the arg min over all possible attributes J of the entropy of your answer given AJ. Right? We calculate this for all, so this is a search or minimization problem. Search over all of these J's and choose the minimum one. Let me write it a slightly different way. Argmax over J of minus HY given AJ. I just put a minus here, so I converted a min to a max. And the next thing I'm going to do is put in a constant that doesn't change over the maximization process, and that constant is going to be the entropy of Y, the unconditional entropy of Y. This doesn't change as you change J, so I can put it in as a constant, right? Doesn't change the result of the maximization. Why did I do that? This should look familiar to you. Remember the formula for mutual information. This is the mutual information between the outcome and a particular attribute AJ. Or you can write it the other way around, it doesn't matter, it's symmetric. So this would be argmax J. So a heuristic would be to choose the one attribute that maximizes the mutual information between that attribute and the outcome. Or, in layman terms, choose the most informative input. Now suppose we did that and we chose one of the attributes, A1 here. Now we're left with some uncertainty here and here, and we need to solve it. And now we'll use your suggestion. Your name, please? Yeah, Mike? We'll use Mike's suggestion of splitting the problem in two. We're going to recursively solve the problem here and here. And this time this is not a heuristic, this is a complete exact solution in the sense that if you minimize this, find the minimal subtree rooted here that resolves all the inputs that sit here, and then do it separately here, you will end up with the minimal general tree. There's no crosstalk between here and here anymore. So you're free to do the best job you can here and the best job you can here and combine the two together. So we're now recursively going to take the examples that came down here, and of the remaining attributes ask the exact same question. Only this time it's going to be all conditioned on being in this leaf. So I'll do it now from now on in terms of mutual information only, not conditional entropy. At this point here, we're going to look for the attribute that maximizes against over all J not equal 1, not equal to the one we already discussed. What is going to maximize? The mutual information between this new attribute J and what? How do you complete this? Y given, thank you. Y. It's still mutual information with Y, but it's now given something. What is it given?
A1.
A1? Not exactly. Somebody else? Not exactly. We're very close. I don't want to put a closing bracket here yet. Please?
Given A1 and AJ.
Not given AJ. AJ is not given because it's here. Remember, we're here. That is stronger than just knowing A1. Yes, A1 equals whatever the value here is. Say V1. V1, V2, V3. These are the three possible values. So it's under condition that A1 equals V1. And then when we find the best choice for here, it would be very similar, but under the condition that A1 equals V3. And in general, when we go down the tree, what we're going to put here is the argmax over all J's not seen yet. We actually don't even have to put the not seen yet in, because considering the ones that were seen already, they won't provide any information because they're all the same once you got here. but in practice we don't need to consider them. So we only consider the attributes that were not seen down this path yet. So argmax over all attributes not seen of the mutual information between this candidate attribute, AJ, and the answer we want, conditioned on everything that is known down this path. So condition on that A1 is V3 and A whatever here is V something, and condition on the path. Okay, so I just gave you effectively an algorithm, a recursive algorithm for constructing a tree. What can you tell me about the algorithm? The first question you should ask yourself is it guaranteed to terminate? Just be computer scientists. Algorithms may not terminate. Is this algorithm guaranteed to terminate? I didn't spell it out for you exactly, but I think you have the gist of it. You keep doing that until the entropy of y at every one of the nodes is 0. Is it guaranteed to terminate?
There's a finite number of attributes as determined.
There's a finite number of attributes, so you can develop all of them.
Yes, the tree is a finite size.
The tree is a finite size. Are you guaranteed that if you considered all the attributes at the end, the entropy would be 0? Remember my caveats from before. I am not telling you if it's hard or easy. I'm not telling you if they are guaranteed or not. Can you think of conditions under which you considered all the possible variables and you still have non-zero entropy of the label? Go ahead.
If you have noise or if you have noise or false negatives that contradict your data that contradict each other, then
Yes.
it will never be 0.
Yes. If you have two inputs that in your list of inputs, let's say D12 and D9 are the same attribute values, the same inputs, but different outputs. So 2 different days with identical weather patterns, and one of them the answer is yes, the other one the answer is no. That could happen if there's noise, namely if either the output was corrupt or one of the inputs was corrupt, or it could even happen when there's no noise, when there's no error. Some functions are inherently stochastic. Some functions, the same input, sometimes will give you yes, sometimes will give you no. We will actually try to learn such functions too, but what we try to learn then is not whether the correct answer is yes or no, but what is the probability of yes under each condition. So when the function is non-deterministic, namely the same input can produce more than one output, or when there's error, you may not be able to finish. So let's say we exclude that. Comment?
But if you constructed a tree that's fully like the full tree of all of the possible attributes, and there's still entropy in some of the leaf nodes, then can't you just say we're done?
Yes.
But I mean, so the algorithm terminates, it just doesn't terminate at 0.
Right. So you can modify it and say, don't continue until the entropy is 0. Continue until you've examined, either you examined all the attributes in every path, or the entropy dropped to 0, whichever one comes first. Okay, so it's a recursive algorithm, and you say until, every node is a recursive call, until entropy is 0 or path is complete. I've examined every attribute. Do this. So the entire algorithm is 2 lines. Until, might as well write it. Entropy of y given path is 0 or path is complete. Complete, by complete I mean all attributes were considered, all inputs were considered. Do, and then you find the value of the attribute to put in here. Then you take all the training examples that used to be here and split them down to the children. and then you ask recursively about each one of these children. Under these conditions, algorithm is guaranteed to converge and stop. Next question you should ask yourself as a computer scientist, okay, it's guaranteed to terminate. Is it guaranteed to give me the right answer? So how do you define the right answer? Let's break it down. Is it guaranteed to give you a decision tree that agrees with the training data? Assume deterministic functions and no noise. I want to see more people moving their heads in the particular committed direction. Yes, yes, it is guaranteed to give you a tree that's consistent with the training data by construction, up to the notion of non-deterministic nodes. Second, is it guaranteed to give you the smallest possible tree that is consistent with the training data? Smallest is measured by the number of nodes. Yes. Anybody else saying yes? I see a couple yeses, a couple no's.
I think it depends on what attribute you start on.
Depends on what?
What attribute you start on.
What attribute to start on? Well, the attribute you start on is the one that is this one, right? I mean, the algorithm is deterministic. It will, you can follow exactly what it will do.
So the algorithm is greedy because it always tries to find an attribute that reduces the entropy most in this point in time. So I wonder if it can get stuck in like a local maximum.
Okay, so the algorithm is greedy. Hopefully you're familiar with that term. It's a greedy algorithm. Greedy algorithm means that in trying to optimize a global measure, like the total number of nodes you'll end up with, it optimizes the local measure, which is how much entropy can you reduce with this one node. Okay? Many times when we're first faced with exponential searches in exponential spaces, which is what we're doing here, we're searching in the space of all possible trees, what we do, one of the heuristics we use is greediness. Try to make a decision that locally looks optimal. Greedy algorithms don't always give us globally optimal results. Very often they don't. So just the fact that it's greedy should bring a doubt to your head. Maybe it will not end up with the best outcome, with an optimal answer. But it's not a proof. Some greedy algorithms do give you optimal results. Depends on the structure of the space. So can you think of examples where this approach will end up not with the shortest possible tree? So I'd like you to think about it. We're not going home yet, but I'm not going to give you the answer. I'd like you to think about it and come up with possibly either examples, an example when this greedy approach does not give you the optimal answer, or a proof, or at least an argument why it always does. Okay? We'll discuss it next time, but let's move on to something else now. These are the kind of questions we will be asking ourselves with every new formalism we discuss. So we'll discuss neural networks next, and we'll discuss other things later on. And the questions are going to be representation power, also known as hard bias, and then search problem. You know, how do you find in the space that you chose, the representation space you chose, how do you find one or more candidates that agree with the training data? And then if you can find more than one, how do you make preferences between them? That's a soft bias. And what would that do for you in terms of generalization? how will that affect how well you'll do in classifying new data? Just keep these questions. These are the sort of the three main questions: representation, search, and generalization. Let me show you the mini example that the book shows using these examples. The book talks in terms of information gain. Information gain is exactly the same thing as mutual information. It's just the book does not have a chapter on information theory, so it doesn't use these terms. This is the exact same 14 examples. 9 of them are positive, 5 of them are negative. The initial entropy, h of y, is 0.940. Remember, I promised you it's less than 1 because it's not balanced. So it's just under 1 bit. Notice that under both conditions of considering humidity or wind, the initial entropy is the same. It doesn't change. And then if you split on humidity, you have 2 possible values. If humidity is high, you have a split of 3 positive and 4 negatives here, and the entropy is very close to 1 because it's very close to 50-50. If humidity is normal, the remaining entropy is close to half a bit, because it's a very skewed distribution, 6 positives and 1 negative, which is what you want. What they call gain here is the mutual information, which is the difference between the original entropy and the weighted combination of the conditional entropies. These are the conditional entropies, conditional on being in this node. You do the calculation here, you do the calculation there, and you find out which has the highest mutual information, and you choose the attribute based on that. Once you chose this attribute, and the one you chose is actually not wind or humidity but outlook, and here you have a node with 0 conditional entropy, so you're done. Here there's still some conditional entropy, and again you are posing the same question, and you build a tree that way. And the reason I'm showing you all of this is there's this very nice illustration of what the algorithm, which by the way is called ID3, does effectively. It searches the space of all possible decision trees, but because it's such a large space, it searches it in a very greedy manner by, at any point, considering a small number of possible extensions. So looking at 2 or 3 other trees, or 5, or however many attributes you're considering, other trees, making a choice among them, going down that path, and forgetting forever the others. So if you follow the bold-faced arrows, it's a search with a flashlight that only can show you 1 or 2 feet around you. Okay, so you look a couple feet around you, you decide which direction to take a step, and then you look a couple feet around you too. This is a classic greedy search. And by doing that, you are growing the tree till you decide to stop. Okay, you owe me an answer to the greediness question. Can you come up with an example when this algorithm will fail to give you the smallest possible tree that agrees with the training data? And if not, why not? I'll see you next time. Oh, there's the decision tree assignment will probably be up today, but you don't have to start it today because we didn't finish discussing everything. It's really meant officially to be started on Tuesday, and you have a whole week to do it.